Well, we have considered moment about an axis in a couple of scalar approaches, and now we're going to consider the vector approach. The vector approach is where we're going to take a unit vector of an axis that we care about, and we're going to dot it, use the dot product times a cross product. If you remember from prior work, when we did dot products, we get a number, just a magnitude. We're going to do the same thing here. We're going to use a cross product, an R cross F. We're going to dot it with a IJK, except that when we get the answer, it will only be a magnitude, just a number. So let's consider this pipe assembly here. We're going to pull it down here with a force. It's going to tend to rotate about in this axis right there. That's the axis that we care about, the AB axis. And when we do that, or when we do the calculation, we'll get a number. We'll just get a magnitude. So let's look at our process. First, we need to find the unit vector of the axis that we care about. And you can see how we've done the unit vector here. And I want to just clarify this a little bit. They call it the unit vector of B, but it's really the unit vector of AB. In other words, in this case, A is at the origin, so it is just the unit vector of B, but the generic or the general case would be where the axis that you care about may not be originating at the origin. So generally, what you'll find is unit vector of AB. Then we need to find the forces. In this case, there's just one force. And then this is the key paragraph right here. The R is a vector from any point on the AB axis to any point on the line of action of the force. So if you look at our picture here, this is our axis, and this is the line of action of the force. And so we have actually 4 possible R vectors here that would make some sense. I'm just going to draw them all for you. You could have one of them originating from here, going all the way to the line of action of the force, or it could go right there. Now the textbook has chosen to use the easiest one, which is right down there, and that's what we'll walk through in a second. But this is also a perfectly good R vector. But also look and notice that the R vector is from any point on the AB axis. In other words, here's another point on the AB axis. So here are 2 other points that could be used for R vector. We could use this one or that one. So in other words, there are 4 R vectors that are very reasonable and very appropriate to use here. They will all give you the same answer, and so we don't really care which one you use. Pick the easiest one for all I care, and that's what the textbook did. So let's just walk through the process here. First of all, we're going to find the unit vector. They're going to choose this 6i. We have the force is negative 300k. The process is you're going to set up the IJK matrix, but in the IJK portion of it here, you're going to put the unit vectors. In other words, when you're going to do this, instead of I, that instead of a J, and this one there, and that comes from the unit vector here. The R is always going to be in the second line, and the force is always going to be in the third line. The way we do the dot product, or the way we do the dot and cross product together, is we're going to say that times that minus that times that minus that times that minus that times that plus that times that minus that times that. Alright, so I know that's kind of mumble jumble, but this is the process that you can use, and in the end it is only a scalar number. The positive result says that it is in the same direction of AB. In other words, it's going in that direction, it's spinning around that direction. By the right hand rule, it is positive in the direction that we have chosen for the unit vector. So what I'd like to do for you, instead of just follow the textbook, I'd like to do one of those other vectors. And this one I'm going to originate from point B. So I'm going to do this one going up like that. And I don't know what we called that, R4 I guess. But if you look at the unit vector of that vector, or look at that vector, it starts at point 4 in the I direction and goes to point 6. So it needs to go point 2 in the I direction, negative point 2 in the J direction, and positive 0.3 in the K direction. So we've got the unit vector of the axis that we care about. Let's go ahead and write our R vector. R equals 0.2i negative 0.2j plus 0.3k. We've already got our f vector as negative 300k. So let's go ahead and set the matrix up. We're going to set the moment about AB is equal to u dot I r cross f. So that's going to be equal to 0.894.4472, 2, negative 0.2, and 0.3. And this was going to be 0, 0, negative 300. All right. And then when we do the dot product, let's go ahead and just write it out. I'm going to stop the video while I do that, and then you can catch up here when I'm done. Okay, I've done the multiplication here, and so again what the process would be 0.8944 times negative 0.2 times negative 300 minus 0.3 times 0, which is 0, minus 0.4472 times 0.2 times negative 300 minus 0.3 times 0, and then this product is going to be 0 because of that. We get the same answer, which of course is always handy when we do that, and it doesn't really matter where you put the r vectors as long as you draw an appropriate one and do it like that. So what I'd like you to do now is pause the video for a few minutes while you work on this one. Again, what we're looking for is the rotation about the AB axis. The force is given for you, so you don't have to do much work there. Find an appropriate r vector, and then do the dot and cross product together. Well, here's the solution to our problem. There are two reasonable r vectors. Remember, the r vector has to go from any point on the line of action of the force any point on the axis that you care about to any point on the line of action of the force. Well, in this case, there's only one point where it makes sense that there would be the line of action. So the ending point for your r vector generally should be at C here, and you can start from the origin or you can start from B. I chose to do B, and so I got r is just equal to 0.4k. The unit vector of AB is 0.6i plus 0.8j. The vector f vector was given here, so just plug that into your matrix, multiply it all out, and you get a magnitude. In this case, it is negative 88. Now, negative 88 would suggest that it is going in the opposite direction of positive AB. In other words, if AB is going in this direction, by the right-hand rule, the negative direction would be going in that direction. If you can just put your fingers and thumb there, you can kind of see that the moment of AB would be going backwards through the pipe. And that makes sense from what we're observing here with the direction of the forces as well, or the force. Now, why is this valuable or useful or important? In many cases in real life, you'll have an axis that may be weak due to either grain or a glue joint, weld line repair, or something like that. So for example, this may be the weak axis here. We just want to find out what the moment might be about that axis. Generally things break because of a moment. So if you put too big of a moment around an axis, then that could be where the fracture or the failure might occur. So again, find out what the unit vector of that axis is, find out what the vector Cartesian description of that force is, and then find a reasonable r vector from any point on this axis to any point on this line of action. And there's quite a few different choices here, so I'm not going to give all those to you. You can figure those out. All right, so good luck with that homework.